Have you ever stopped to think about what happens behind the scenes when you hit play on a Netflix show? It doesn't matter if you're curled up on your couch watching on a smart TV, commuting with your phone, or even soaring on a flight 30,000 feet above ground, Netflix just works. That instant stream, the crisp HD picture, and the lack of buffering feel like magic. But it's not magic. It's the result of one of the most advanced and meticulously crafted streaming infrastructures in the world. Think about this. Netflix serves over 230 million users globally. That means millions of people could hit play at any given moment on all kinds of devices and from all corners of the world. Still, they all experience fast load times, uninterrupted viewing, and adaptive quality based on their network. This scale is unprecedented, and it demands a level of engineering most companies only dream of. So how does it all work? It starts the moment Netflix acquires or produces a piece of content. That video file goes through intensive processing, being transcoded, encoded, packaged, and stored in multiple formats and bitrates. The goal? Deliver the optimal version of the video to each user based on their specific device and connection. And it doesn't stop there. Netflix has built its own content delivery network, known as OpenConnect, to bypass the inefficiencies of the public internet. These OpenConnect appliances, or OCAs, are servers placed within local ISPs and edge locations. This brings the content physically closer to the end user, cutting down on travel time and internet congestion. Meanwhile, adaptive bitrate streaming ensures that if your network weakens mid-show, the video doesn't freeze. Instead, it quietly switches to a lower quality stream to keep things moving. Combined with smart software on every device, Netflix maintains a constant watch on playback conditions and adjusts dynamically, almost like cruise control for streaming. So yes, while it looks like you're simply watching a show, you're actually engaging with a global, intelligent, highly scalable video platform. And today, we're going behind the scenes of this marvel to explore exactly how Netflix streams seamlessly to millions around the world. Streaming at Netflix's scale isn't just about uploading a video to a server. It's about orchestrating a massive system that handles performance, scale, and user satisfaction, simultaneously and in real time. First, there's the challenge of massive scale. Netflix isn't serving a few hundred or even a few thousand viewers. It's streaming content to hundreds of millions of users worldwide. That means billions of hours of video are streamed every month. The system has to work 24/7 without fail across every continent, supporting simultaneous requests from users in Tokyo, Sao Paulo, New York, and Johannesburg. Next is low latency and high quality. When a user hits play, they expect the video to start instantly, not in a few seconds. Right now, that requires a global system that minimizes delay at every step, from the server delivering the video chunks to the decoder rendering frames on a screen. It must balance speed with quality, delivering HD or even 4K video with minimal buffering or compression artifacts. Then comes global delivery. Netflix must ensure content reaches every user, no matter where they are. To make this work, they've built a custom CDN called OpenConnect. It helps bring content physically closer to users by deploying local cache servers, reducing internet backbone traffic and ensuring faster response times. This system must also accommodate peak usage spikes, like a new season launch or global events. Another core challenge is being adaptive to bandwidth conditions. Internet connections are unpredictable. You might start watching on fast home Wi-Fi, then switch to mobile data while commuting. Netflix has to dynamically adjust the video quality based on available bandwidth without interrupting playback. This means encoding every video into dozens of bitrate variants and allowing the player to switch between them smoothly in real time. Finally, device compatibility. Netflix has to ensure smooth playback on everything from a $100 Android phone to a $3,000 smart TV. Each platform has different capabilities, resolutions, codecs, and software environments. Netflix's engineering teams build custom SDKs and optimize playback for each device type, ensuring a consistent experience regardless of where or how you watch. In short, Netflix isn't just playing a file. It's solving a set of intertwined technical challenges involving scalability, reliability, quality of service, and user experience, all at a global level. Let's walk through the journey of a Netflix video, from the moment it's received to when it's streamed to your device. It all starts with content ingestion. This is when Netflix acquires a show or movie, either through studio partnerships or its own original productions. The raw video file is large and uncompressed. Before anything else, it's encrypted to protect the content and then uploaded into Netflix's storage and processing pipeline. Next comes transcoding. This is a critical phase. The raw video isn't ready for streaming in its original form. Instead, it's broken down into multiple formats and resolutions to accommodate different devices and internet speeds. This is where Netflix's per-title encoding comes into play. Instead of using a fixed bitrate ladder for every video, Netflix analyzes each title to find the optimal settings based on the complexity of its scenes. A slow-moving documentary requires different compression compared to an action-packed movie. This technique ensures better quality at lower bit rates, saving bandwidth without compromising the viewing experience. Then we move to packaging. Netflix uses streaming formats like HLS, HTTP live streaming, and MPEG-. These formats are designed to break the video into tiny chunks, each lasting 2 to 10 seconds. Why? Because this enables adaptive bitrate streaming. Your device can seamlessly switch between different quality levels chunk by chunk, depending on the current internet speed. Each chunk is encrypted, labeled with metadata, and stored in content delivery servers. Netflix doesn't store the video as a single massive file. Instead, it becomes thousands of mini files, sliced, compressed, and ready to serve instantly. So, when you hit play, Netflix isn't just serving a file, it's intelligently streaming the most appropriate chunks, resolution, and bitrate in real time. This pipeline, from ingestion to encoding to packaging, is what allows Netflix to deliver seamless playback to any device, under any network condition, anywhere in the world. Now let's look at one of the most brilliant systems Netflix has built to handle global content delivery, their custom content delivery network called OpenConnect. In most streaming platforms, content is hosted in centralized data centers or through third-party CDNs. But Netflix took a bold, forward-thinking approach. They built and now operate their own CDN. The heart of OpenConnect lies in what Netflix calls OpenConnect appliances, or OCAs. These are high-capacity servers that store the most popular Netflix content, not in some distant data center, but inside the networks of internet service providers, ISPs, around the world. Think of it this way. Instead of making every viewer fetch a movie from a central server thousands of miles away, Netflix puts a copy of the most watched content right next door. It's like placing a copy of your favorite show next to your Wi-Fi router. These appliances cache high-demand titles locally, meaning when you hit play, the stream doesn't travel across the internet. It comes straight from the nearest OCA inside your ISP. This reduces buffering, improves start times, and lowers the load on the global internet. Netflix strategically deploys thousands of these OCAs worldwide, especially in regions with high traffic or limited connectivity. They work closely with ISPs to install these servers for free. In return, ISPs benefit from reduced transit costs and better performance for their subscribers. OCAs also help during major traffic spikes, like when a new season of a popular series drops. Instead of overwhelming Netflix's central infrastructure or clogging internet backbone routes, the OCAs handle most of the traffic right at the edge. By cutting out the middlemen and going directly into local networks, OpenConnect gives Netflix unparalleled control over the delivery pipeline. It's what enables them to maintain consistent video quality and fast performance, even when millions are streaming simultaneously. OpenConnect is one of Netflix's biggest infrastructure advantages, and a key reason why their streaming remains fast, reliable, and buffer-free almost everywhere on Earth. One of the most underappreciated technical marvels behind Netflix is its device compatibility. The platform supports over 1,000 types of devices, including smart TVs, game consoles, streaming sticks, smartphones, tablets, laptops, and even set-top boxes. Each of these devices has different hardware, operating systems, screen resolutions, processing capabilities, and supported video codecs. Yet Netflix delivers a consistently high-quality experience across all of them. To make this possible, Netflix builds and maintains custom software development kits, SDKs. These SDKs are embedded directly into many smart TVs and devices during manufacturing. By working closely with hardware partners, Netflix ensures deep integration, giving it low-level control over playback behavior, performance, and even remote firmware updates. This enables Netflix to fine-tune video delivery and quickly fix bugs, ensuring optimal performance on even the most resource-constrained devices. But it's not just about compatibility, it's about optimization. When a user hits play, Netflix's backend assesses the device's capabilities. Can it support 1080p or 4K? What kind of decoder is available? H.264, VP9 or AV1? Does it have HDR support? This information is then matched with the user's current network conditions to determine the best possible stream. This is where Netflix's adaptive bitrate streaming comes into play. Instead of delivering a fixed video file, Netflix serves the content in small segments of varying quality levels. Based on real-time feedback, the Netflix app on your device dynamically switches between these segments. If your internet is strong, it may choose a 4K stream. If the signal weakens, say you move farther from your Wi-Fi router, the stream smoothly switches to 720p or even lower without ever pausing or buffering. Even the user interface is optimized per device. On a PlayStation, you get a different UI layout than on an Android phone. On smart TVs, navigation is adapted for remote controls, while on phones, it supports gestures and touch. This kind of context-aware design ensures the app feels intuitive and smooth, no matter where it's being used. Another important factor is bandwidth efficiency. On mobile networks, data usage is critical. Netflix gives users the option to cap video quality or download content in advance. Advanced compression algorithms, like those used in AV1, are selectively deployed to squeeze the best quality into the smallest possible data footprint. This meticulous attention to compatibility and performance means Netflix doesn't just stream the highest quality, it streams the most appropriate quality for your situation. Whether you're watching on a budget phone with spotty cellular coverage or a high-end 4K HDR television on a fiber connection, Netflix adapts to you. That's why the experience feels seamless and personalized, because it is. Adaptive bitrate streaming, ABR, is a crucial technology used by video streaming platforms like Netflix, YouTube, and Amazon Prime Video to ensure smooth and uninterrupted playback experiences across varying network conditions. Instead of streaming a single, fixed quality version of a video, ABR dynamically adjusts the video quality based on the viewer's current internet bandwidth, device capabilities, and other real-time factors. At the core of ABR is real-time bandwidth estimation. When you begin watching a video, the player quickly assesses your network speed and selects an appropriate video quality to match it. The video is broken into small segments or chunks, typically lasting 2 to 10 seconds each. For each chunk, the player can choose from several available quality levels, low, medium, high, or even ultra-high definition, depending on the bit rate your connection can currently support. Bitrate in this context refers to the amount of data transmitted per second of video. Higher bit rates mean higher quality video, but also more data that needs to be delivered over your network. If your network is fast and stable, ABR selects a higher bitrate stream with better resolution and detail. However, if your bandwidth drops, ABR seamlessly switches to a lower bitrate version of the video. This process of bitrate switching is continuous and automatic. As shown in the slide graph, the bitrate can vary throughout the playback. It may increase when your internet improves or decrease when there's congestion or signal loss. The viewer rarely notices these switches because they're designed to be subtle and to happen between video chunks. You might see a slight drop in resolution, but you'll almost never encounter a pause for buffering. A key component enabling this smooth transition is buffering ahead. The video player keeps several seconds of content preloaded in a buffer. This preloading creates a cushion that absorbs brief network hiccups without interrupting playback. As long as the buffer has enough content, the viewer will not see loading spinners or frozen screens. When network quality improves, the player may start buffering higher quality chunks again. At the heart of Netflix's architecture is a microservices model hosted on Amazon Web Services, AWS. Instead of one giant application doing everything, Netflix is broken down into hundreds of smaller, specialized services. Each microservice is responsible for a specific task, whether it's streaming a video, validating your login, processing payments, or recommending your next favorite show. These services operate independently, which means a failure in one doesn't bring down the entire system. If the recommendation engine fails, you can still watch your video. If the payment system is overloaded, your current session won't be affected. This independence provides flexibility and makes updates safer, faster, and easier to roll out. Imagine if your show stopped every time a server crashed. Netflix can lose entire data centers, and you'd never notice. It's built to expect failure and recover from it automatically. To keep everything running smoothly, Netflix uses real-time monitoring and alerting systems. These tools constantly check the health of services, watching for issues like high latency, errors, or unusual spikes in traffic. If something goes wrong, the system can alert engineers instantly or even trigger self-healing mechanisms that automatically restart services or reroute traffic. Scalability is also baked in. As user demand spikes, say during a new season release, the system automatically scales up resources to handle the load. When demand drops, it scales down, saving resources and cost. In short, Netflix's backend is built not just to work well, but to work even when parts of it fail. This is what allows it to deliver a consistent, reliable streaming experience at global scale. And that brings us to the end of our deep dive into how Netflix streams to millions of people around the world, reliably, smoothly, and intelligently. We've explored how adaptive bitrate streaming ensures you never see a buffering icon, how microservices keep everything modular and resilient, and how a global, fault-tolerant cloud infrastructure can survive entire data center outages without missing a beat. From real-time monitoring to automatic scaling, everything is carefully engineered to make sure you get a seamless experience. Whether you're watching on a 4K smart TV or streaming on your phone in the back of a moving train. Let's quickly recap what we learned. Netflix uses adaptive bitrate streaming to adjust video quality in real time based on your internet connection. Its architecture is made up of microservices, each doing one thing well, hosted on AWS. The system is fault-tolerant, running across multiple regions with built-in failovers. Real-time monitoring and self-healing systems ensure problems are detected and fixed instantly. And it all scales automatically, handling everything from quiet weekdays to global release days. Pretty amazing, right? If you enjoyed this behind-the-scenes tour of Netflix's engineering marvel, do us a quick favor. Hit that like button. It really helps this video reach more people who are curious about how tech works. Subscribe to the channel if you want more system design breakdowns like this one. We've got plenty more coming, from cloud infrastructure to app architecture and beyond. And now it's your turn. Drop a comment below and tell us, which system should we break down next? Should we reverse engineer YouTube and see how it delivers billions of videos daily? Or maybe take a ride with Uber and explore how it matches drivers and riders in real time? Or dive into the world of Instagram and learn how it handles image processing, feed ranking, and stories at scale. Let us know what you're most excited to learn about next. We're always reading the comments and building our next episode based on your suggestions. Thanks again for watching. We hope you're walking away with a deeper appreciation for the tech that powers your everyday apps, and maybe even a bit of inspiration to design something great yourself. Until next time, stay curious, stay creative, and we'll see you in the next one.